Good morning. Today we're going to be looking at Chapter 13. We're going to be looking at the physics of fluids. So up until now, almost all the objects that we've looked at have been solid, right? They've been blocks going down inclines, textbooks being set on tables. But now we want to go in and look at the physical properties of water, of air. So let's take a look. Now, first of all, let's think about phases of matter. It's very common, the three common phases: solid, liquid, gas. Solids have a definite shape. They're rigid in size. Liquids do have a fixed volume. Liquids are not easily compressible. Like water, water can be poured from one container to another. It can change its shape. But its volume, it's very difficult. We have to push with a lot of force to compress water very much, a liquid. Gases, on the other hand, typically, things like air can be very easily compressed. So gas is easily compressed, liquids not so much, and that's what we're going to be looking at in this chapter when we look at fluids. A couple of properties that are going to become very, very important for us. The first of those is density. Now, density we've looked at from time to time is defined as mass per volume, and the standard units for density would be kilograms per cubic meter. So density also, it's going to be useful to write these densities as grams per cubic centimeter. Those are handy too, and there is a factor of 1,000 between those. So I think we'll see some examples of units conversions, but definitely pay close attention to the units with density and with pressure. Make sure that you're staying with standard units when you're doing calculations, so that standard units in, standard units out is kind of the approach we want to take. Water has a density of 1 gram per cubic centimeter. Here's one of those conversions right here. So cubic centimeters are like this big. So cubic centimeters, centimeter by a centimeter by a centimeter, and that much water has a mass of 1 gram, and that's actually how the grams are defined. So they're defined in terms of the density of water. Now, if I take a cubic meter of water, a cubic meter is this big by this big by this big. That's a lot. A cubic meter is 1,000,000 cubic centimeters, right? There's 1,000 cubic centimeters in a liter. There's 1,000 liters in a cubic meter. So remember, remind yourself, a cubic meter is big. A cubic meter is a really good sized volume. And so when we do the conversions of both centimeters into meters and grams into kilograms, it turns out that if I have a cubic meter of water, its mass is 1,000 kilograms. That's a ton of water, a metric ton of water. So that's a big difference. Now, this word specific gravity, which I wish we wouldn't use, but we do, you've got to be prepared for that. Specific gravity is the density of something relative to the density of water. So if I have a specific gravity of 7, then that material is 7 times the density of water. It's just a ratio that we work in terms of. All right, let's try an example here with density. What would be the mass of a block of iron? It's a sphere, I guess. It has a radius of 18 centimeters. So, diameter of 36. It's like this big. It's iron, and it's solid through and through. So here's a picture of that. Here is my block of iron. There is the radius. Here is the word iron. And I looked up the density. All right. So I looked up the density of iron, and it was listed as 7.874 grams per cubic centimeter. I don't know how much variation you see with different types of iron and how they've been produced, but anyway, this was a number that I found. And so what I did was I converted that, and here's an example of going from grams per cubic centimeter into kilograms per cubic meter. So first of all, 1,000 grams is 1 kilogram. That cancels the grams. Now for the centimeters, 100 centimeters is a meter, and that gets cubed. So this becomes 7,874 kilograms per cubic. So you can see how that works. It's a factor of 1,000 when we convert grams per cubic centimeter into kilograms per cubic meter. Now, for the density here, we're going to need to get the, what was the other formula we want to use here? We got the density. Oh, we want to find the mass. So the mass is density times volume. We've got the density determined. We just have to come up with a volume. Now the volume for a sphere is 4/3 pi r to the third power. So they've given us the radius. We can plug those numbers in. Now the 18 centimeters need, oh, I left it as I did. Okay. Anyway, I left the volume in terms of centimeters. So this is 24,429 cubic centimeters. And then I can use this density. Actually, that will work. So when I do the mass, I can do density times volume. The density of 7.874 grams per cubic centimeter times the volume left me with a mass of 192,350 grams. And then I just converted this into kilograms. So it worked out to be 192 kilograms. That's a lot, right? But it's a pretty good sized piece of iron, and iron has a pretty large density to it. And so that's where those numbers are coming from. All right, now the other property that we're going to be working with quite a bit is pressure. Pressure is defined as force per area. Now that's, P is not power, it's pressure, so don't get those mixed up. Pressure, it says, is a scalar. The units of pressure are going to be newtons per square meter. So newtons per square meter. Now, those, a newton per square meter of pressure is 1 Pascal. So there is a unit that goes by that name of Pascal, and that's going to be the same thing as 1 joule per cubic meter. So if I take the newtons, multiply that by meter, and so if I multiply the numerator and the denominator by meters, what I get is joules on top and meters cubed below. So I added this in. Pressure can also be written as an energy density. So something under high pressure is actually storing energy, because when you release the pressure, the material can push back. So it can transfer, and if you pack something in and created something under high pressure, that represents energy that you've stored in that high pressure material. So Pascal's works, that's standard. It's equivalent to a newton per square meter. It's equivalent to a joule per cubic meter. Those are the units. Now there's a bunch of other units of pressure, and so we'll talk about those at some point. But the standard units are what you probably want to stay in terms of, at least when you're first working with these problems. Now, a couple things to remember with pressure is that pressure is an intensive property of the material. Pressure exists all through the material. And so here's a sample of water, and there's water pressure. The water pressure is there due to the presence of air pressure, and then also as you drop down below the surface, the water pressure builds up because layers of water are sitting on tops of layers of water, and gravity pulls all those together. So all of these fluid pressures that we're talking about, air pressure, water pressure, it traces back to Earth's gravitational forces. Gravity squeezes the entire planet. So everything just has a certain pressure to it, depending on how deep into the atmosphere or how deep into the oceans or how deep into the solid material of the Earth the pressures are going to go up because of the gravitational effect. So this is showing that pressure exists at every location. Forces due to pressure, because of gravity, the pressure from below actually is a little higher than the pressure above, but the pressure is in all directions. So they're saying it's the same pressure in every direction. That's not quite true. As you drop to lower elevations, the pressure does go up. But the pressure is throughout the material. The pressure exists at every location. If we drop something into a fluid, something in air, I mean, I'm in the air right now and I'm experiencing air pressure from every direction surrounding me. If we drop something in the air, drop something in the water, that pressure is going to be present throughout. All right, and it's a good thing the pressure is there. You know, that we have all of this atmospheric pressure at the surface of the Earth. That's about 101,300 pascals of pressure. It's a lot of pressure, but everything is experiencing that pressure. So, for example, liquid water won't exist at low pressure. The liquid phase for water is not possible. There has to be a minimum pressure at which water is liquid, that it has a liquid state. And if you're familiar, if you've followed at all the searches for life on Mars, one of the issues right now is, of course, maybe hundreds of millions of years ago, Mars' atmosphere had a much higher pressure, and that meant that water would go into liquid form. But at the current pressure on the surface of Mars, liquid water is not an option. You can have water vapor, you can have solid water, you can have ice if the temperature drops enough, but liquid water doesn't exist at those low pressures. So pressures, you know, it's just everything around us is at some sort of fluid pressure. Okay, now this is actually going in and showing how that fluid pressure is going to increase. And what they're saying is we can think of it this way. We can think of starting at the surface of water, dropping down a distance h, and then calculate how much mass would be present in all that. And that mass is going to be sitting on top of the water below it. And we can show that the pressure as we drop down through a fluid, not just water, but the pressure dropping down through a fluid is the density times the gravitational field times the depth. That works for air, that works for water. Now, for water, the density of water remains roughly the same. Water is not very compressible. So if you're dropping through water, the density is roughly the same, and we can use this formula directly. If we're dropping through air, we have to take a more detailed look at this because the density is not constant. And you know this from going up to high altitude, air pressure drops dramatically compared with at the surface. Whereas for water, the air, not just the air pressure, but the air density drops as you go to high altitude. So the density will vary, and we'll see that the density for air is related to the pressure of the air at that location. So, all right, let's see how this formula comes about. So if we take, now it doesn't have to be water at the surface, let's just pick two different elevations within the fluid, and it doesn't have to be water. But so here is a depth into some fluid. Now there's pressure from below, there's pressure from above, and those pressures are going to generate forces from above and forces from below. Now the fluid itself, and you can think of this as water works fine, will have some amount of mass, and so there's a gravitational force pulling down on that water. What that leads to is higher pressure from below. So let's start with the force diagram here. The force from below needs to be equal to the force from above plus the additional force due to gravity. So there's the gravitational effect as we drop deeper and deeper. Now what I can do is I can take the force and divide by area, divide everything by area, right? That works. Now the area we're thinking of is the cross-sectional area of that sample of fluid. So there's a cross-sectional area that's horizontally placed. There is a vertical height or depth. I guess we're using H to represent both. So the volume we're looking at of that fluid is the cross-sectional area times the height. And it's a rectangular box of some sort that we've outlined. Now, force over area, that's pressure. Force over area from above, that's the pressure from above. And then here we have mg over A. So what that leaves us with is the pressure from below equals the pressure from above plus, now the mass can be rewritten as the density times the volume. So here we go, there it is. Mass is equal to density times volume. And so volume is cross-sectional area times height. And I can substitute all of that in. And so here I can cross out the cross-sectional area, and it says that the pressure from below equals the pressure from above plus rho GH, and that's where that formula comes from. So here is the derivation of the formula that they have. We've filled in a lot of steps. They did a very rough view of that. Now, for short distances, we can say that dP, the amount of the pressure varies over a short distance, times the local density, the density of that location, times g, times dx. And that provides us a way to calculate pressure differences in air, for example. So in air, what we can do is come up with a formula telling us how the density varies. You know, the density is going to drop off as we go to higher and higher elevations, and we can calculate pressure differences based on that. And that's what they're showing here in this diagram also. They're showing that when we get down to really thin layers here, they're calling it dy. I'm using x. I tend to use x. I have better luck. I don't want to call it luck. I have a better success rate using x than y. I know it sounds crazy. But here is dy and y. That works fine. Anyway, it's the pressure as we drop down, the pressure. Where is y located? Oh yeah, they're starting at the bottom. Okay, they're starting at the bottom and working up. So they're saying as y increases, the pressure drops off. You could do this in either direction. If you reverse the coordinate system, that becomes a plus sign if you're thinking how does the pressure increase as we drop down versus how does the pressure drop off as we move upwards through the fluid. And again, it's gravity creating this effect. Okay, and they're setting up this in a little bit more detail. So they're saying here is a point at the bottom of some container. Here is a pressure at some location, y1. Here is some pressure at the top. And what they're saying is you can integrate through the fluid to carry out this pressure difference. So the pressure difference then would come from following this integration. Now we'll come and look at we do want to come back and look at an example with air pressure. Air pressure is probably a useful one to look at because it's so familiar. It's handy to be able to think about what determines the rate at which air pressure and air densities drop off with altitude. All right, let's see. You know, when I'm driving through the Central Valley, it seems like every town you come to, they've got a big water tower up on top of this pretty large tower that they've built. And I always wondered, you know, why is there a water tower? Why are we storing water up in these towers? Can't you just store the water down on the ground somewhere? And you know, the town name is always written on that, and I thought maybe it's a way to advertise the town, build a water tower, put it up really high, and let everybody driving by know the name of the town. And then I took physics, and you know, and now I understand this better. The reason to put the water up high is to create pressure in all of the water pipes throughout the town. So what happens is, you've got a water tower, you build it, you put it up on this really high structure on the tower, you build a water tank and put it up on the tower. This one is listed as being 30 meters in height. Now, that's measured from the top of the water down to, now they've measured this at the elevation where it's being used inside the house. So we've got 30 meters of height. What does that do for us in terms of water pressure? Now, I set it up a little differently. I measured from the top of the water down to the water that's in the water main running through the streets. Now, oh no, I set it up the same way, never mind. H comes down to here, and this is the elevation of the first floor of a building. And what we want to know is, what will the water pressure be at that location? Now, the water pressure, the pressure of the water is going to depend on how much we drop below the surface. Now, at the top of the water inside the water tank, that's atmospheric pressure. So that is open to the atmosphere in terms of pressure. And so there's already a pressure of 1 atmosphere at that location. Now, 1 atmosphere of pressure is equal to 101,300 pascals. So, you know, roughly averaged over the, you know, surface of the Earth, the atmospheric pressure at 0 elevation is that number. And so that's what we use as a conversion. So 1 atmosphere of pressure is this. Now, this is the standard unit in pascals. The 1 atmosphere is kind of handy, I think. That's my personal opinion, is that working in terms of atmospheres can be useful, but when we're doing calculations, we want to get those numbers back into pascals. All right, so what will the water pressure be down in the water main under the street, or at the height of the house, I guess is what we decided. So I'm going to drop down. I'm already at 1 atmosphere of pressure. I'm already at 101,300 pascals. And then I want to add on additionally rho GH. So this is, the density of water is 1,000 kilograms per cubic meter. The gravitational field of Earth, 9.80 newtons per kilogram. And then the depth, or the height, that we've dropped through the water is 30 meters. Now, dropping through water 30 meters is going to add on an additional pressure of 294,000 pascals. So that's pretty impressive. Notice that coming all the way through Earth's atmosphere. Now, you know, that's like 100 kilometers of atmosphere. Now, the atmosphere up high is really thin, so that's not much of an effect. But as you get closer and closer to the ground, the atmospheric pressure becomes fairly significant. 101,300 pascals, that's a lot of pressure. But going through 30 meters of water, vertically dropping, builds up an additional 294,000 pascals. So that's almost 3 additional atmospheres of pressure, right? We go from 1 atmosphere, drop through the water, and build up almost 300,000 pascals of additional pressure. So the total pressure then inside the house is at 395,300 pascals. That's what's called absolute pressure. Now, if I open a faucet inside the house, the water comes shooting out, and that's because they built the water tower. If they had built the water storage on the ground, the water would not come shooting off out of the faucets. So now the water main from the tower goes everywhere, goes all the way through the city. You know, anytime a new building is built, they make an additional connection to that water main. And so whatever pressure this is being maintained at because of the tower, that pressure applies, it works, it has its effect on everywhere we attach a pipe. All right. Now here in the Bay Area, we don't have water towers, and that's because we have hills. So you can build reservoirs up at the tops of the hills and create the same effect. So if you're hiking around or if you're biking around in the hills or something, every once in a while you'll see these reservoirs of water, you know, let's say East Bay mud or something like that, are storing the water and maintaining the pressure. As long as water is saved in those, at those higher elevations, that maintains water pressure for us. Okay, so these local reservoirs around in the hills, that's not so much water storage as it is maintaining pressure in our pipes. So the water comes shooting out forcefully. If you measure the pressure, again, there's this difference between absolute pressure and gauge pressure. And if I open up a faucet, you know, my house is not at zero pressure, it's at atmospheric pressure. So gauge pressure specifically refers to how much overpressure did we create. So we created this additional overpressure of 294,000 pascals, and when the water shoots back out into atmospheric pressure, this is the amount of pressure difference driving the water out of that pipe. So good to know, all those water towers. Now, what you might be wondering is, wait a minute, sure, coming down with water for 30 meters builds up an additional 294,000 pascals, but what about air pressure? Doesn't air pressure continue to increase as we come closer to the, you know, closer to the ground or lower elevations? And absolutely. So the air pressure also is going up. Let's go ahead and calculate that. So if I start at the top of the water here and make my way through the air, not through the water, the increase in pressure then, rho GH, it's the same gravitational field, it's the same height, the density is different. Turns out that air density at the surface of the Earth at 20 Celsius is about 1.20 kilograms per cubic meter. Now that's not nothing. When you think about it, if you have a fairly large room and every cubic meter, you know, there's a cubic meter, how much air is in that cubic meter? And I would guess none or a few grams, but it turns out it's 1,200 grams of air. 1,200 grams of air in every cubic meter of air, right? That's a lot. So if we took all the air in this room and condensed it down into a liquid, put it in a container, you wouldn't be able to lift it. You know, the air has a significant amount of mass, and I know when we walk back and forth through the air, we think, there's not much mass here, come on, how much mass could there be? So, you know, that's not zero, that's something. So 1.20 kilograms per cubic meter, when I multiply that through, the pressure increase is only 353 pascals. So what we can see here is that the water is something like 800 times denser than air. And so for the same elevation drop, it builds up pressure 800 times faster. And so whereas air pressure goes up by a few hundred pascals, water pressure goes up by a few 100,000 pascals. So what you find is in a lot of these examples, we just ignore the increase in air pressure if it's being compared with something like water. All right, but I always think it's good. I think it's a good exercise, and that's why I've included that here, to go back and go, okay, how much of an effect are we getting? How much are we ignoring when we ignore the effect of air pressure? And in this case, it's only a few hundred pascals. It's not much. All right. So here we are, example 13.5. We are looking at variations in air pressure. All right, this is a bit challenging. You're not expected to recreate all the steps on this, but I think it is useful to think about how air pressure and air density drops off as a function of elevation. So let's take a shot of this. First of all, let's get familiar with air. Earth's atmosphere is 78% nitrogen. Now those are N2 molecules, two nitrogens stuck together. About 21% of the molecules are O2. Those are two oxygen atoms attached, chemically bonded. Argon makes up about 1% of the atmosphere. Now argon is chemically inert. It's a noble gas, it's an inert gas. But what you're breathing is, well, it's primarily these four items. So nitrogen, oxygen, argon. Now those add up to 100. What we've left out is water, and water is variable. If you go to a very, 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 very dry location, basically you can find locations where there's almost no water at all in the air. These are not liquid water, this is vapor water in the air. On the other hand, if you go to a place that's really, really, really humid, water could make up as much as 4% of the molecules in the air. So this is a variable that we have to figure in, and then these guys have to adapt to that. So here are the components of dry air, and then here is the water. Now, what's always surprising to me is the carbon dioxide levels are so low compared with the other constituents of air. So carbon dioxide only makes up about 400 parts per million. So 400 parts per million would mean I would have to search through 10,000 air molecules, go through the air molecules and count them. Okay, there's a nitrogen, oxygen, there's an argon, there's another nitrogen. I would have to go through 10,000 on average to find 4 carbon dioxides. Just 4 carbon dioxides per 10,000. How do the plants do that? Plants are using sunlight as an energy source to take carbon dioxide from the air and build all kinds of organic molecules from the carbon dioxide. They have to search through a lot of air molecules to find those carbon dioxides. They're very diligent that they're able to do that. So yeah, carbon dioxide is at 400 parts per million. Now in terms of photosynthesis and autotrophs, plants that are able to generate their own compounds that they need, the carbon gets made into sugars, it gets made into proteins, it gets made into amino acids and then into proteins, it gets made into lipids, gets made into nucleic acids, just everything carbon-based, and that's all coming from carbon dioxide that they have to sift through to find. Now on the other hand, in terms of geophysical properties, in terms of global warming, that level of carbon dioxide, it's significant. So you can see that that's a very low level. We need to keep it at that low level. If you take a planet, just for comparison, like Venus, Venus has an atmosphere that's like 100 times denser than Earth, and it's predominantly carbon dioxide. Now, early on, we believe, all the evidence suggests that early on Earth's atmosphere, hundreds of years ago, hundreds of millions of years ago, or billions of years ago, Earth's atmosphere was predominantly carbon dioxide. Where did all the carbon dioxide go? And on Earth, the carbon dioxide dissolved into the water. there was plenty of water and carbon dioxide around. The water formed big puddles of liquid we call oceans, and the carbon dioxide dissolved, and from there it turned into rock. So at this point in lecture, 20 years ago, 30 years ago, when I was first, 25 years ago, when I was first teaching, at this point I would pick up a piece of chalk and say, here is Earth's carbon dioxide. It's calcium carbonate, right? So some of that carbon dioxide turned into rock material. Some of it has turned into shells of animals. So the carbon dioxide, little by little, drawn out of the atmosphere, dissolves in the ocean, and then gets turned into other compounds. Venus didn't have that. Venus was at a higher temperature. Oceans probably did not form, and as a result, Venus eventually lost most of the H2O molecules. Those are very low mass. If you look at molar masses, water, H2O is pretty low. A lot of that water was lost probably into space. Nowhere for the carbon dioxide to go, stayed in the atmosphere, and as a result, surface temperatures on Venus are the highest in the solar system, of any of the planets, are the highest temperatures in the solar system. So we don't want too much carbon dioxide. So we want to limit this, and Earth's carbon dioxide levels have gone up significantly. So if you look over the past 100 years, it's gone from 300 parts per million to 400. And that rate is just picking up all the time. So that's certainly something we have to pay attention to in taking care of the planet. All right, let's say this is air. And then I'm going to bring in something, maybe you guys have seen this. A lot of times in Physics 3A, students have had chemistry. They have a strong chemistry background. If not, that's fine. You're not required to do that at this time. But there's what's called the ideal gas formula that says for gases, the pressure, volume, temperature, and number of moles of gas can be related with this formula, where big R is called the gas constant. Anyway, so I'm going to go through this quickly because you guys don't have to be familiar with this anyway. What we can do is we can take the ideal gas law. We can say that the number of moles in the sample is the mass divided by something called the molar mass. Now, the molar mass is based on the masses of N2, O2, argon, and those are the ones I'm going to use. So we can get a molar mass for air. We can average over those molar, or get a weighted value of the molar mass. That gives us PV equals big M over little m times RT. And then what we can do is we can actually get a formula for the density of a gas. The density of a gas is given by the local pressure, so it's directly proportional to pressure, depends on what we call the molar mass, how heavy are the gas molecules, divided by this constant that we have the value of and the temperature. Now what we can do then is, remember this was the formula we said we could use to calculate how the pressure drops off as we go up. So we start at the level of the surface of the Earth, and we start going up through the atmosphere, and this is going to tell us how the density drops off. Now what we're going to do is take the density here and substitute in PM over RT. So I'm going to substitute that into our formula. The reason for that is right now I have pressure on this side. I want to keep track of how the pressure drops off with elevation. I have height on the other side. Density, it's too many variables. So I needed to get density in terms of pressure. And then what we can do is we can set up an integral. So I can bring all the p's to one side. The mg over RT remains on the right side. And then the dx is keeping track of elevation. So let's integrate. So I can take the dp over p. I can integrate that from the pressure at the surface to some pressure at a higher elevation. that's equal to minus big M times G over big R times T, temperature. I'm going to integrate that from ground level up to some higher elevation. Now the dP over P gives us a logarithm of pressure. Evaluating logarithms will give us a logarithm of pressure over atmospheric pressure. P naught is the pressure at the surface. And then this side is telling me the rate at things are dropping off, minus mg over RT times x. Then I exponentiate and bring the P naught to the other side. It says that the pressure, as we go up through the atmosphere, will be equal to the pressure at the surface times an exponential. So that's the important part here. It drops off exponentially. Density and pressure of air, they don't drop off just linearly, they drop off exponentially as you go up higher. Now what that graph is going to look like then, if I do pressure here, as a function of height, I'll put that in meters, pressure in newtons per meter squared. I'm going to start off at P naught, atmospheric pressure, and then it's going to drop off exponentially. Now what I would like to know is how fast does it drop off? So to do that, what we can do is, right here, I introduced this scaling factor. So I set up the constant A. Now, looking at the formula here, I can say that A is equal to RT over mg. So I wrote that out. The scaling factor, which tells us how fast air pressure is going to drop off, how fast the density of air drops off, is going to be given by RT over mg. I plugged those numbers in. Now, just to let you guys know what I used Earth's gravitational field. I used what's called the gas constant. We'll see this later this semester when we get into thermodynamics. We're going to be working with more with the gas constant, so we'll see that. Now the temperature, I used 0 Celsius, which is because I know if you get up in the atmosphere, it's going to be much lower temperature than it is at the surface. In fact, that's probably too high. But I went with 273 kelvins, and I'm guessing you guys are familiar with kelvins as temperature units. If not, that's fine. We'll pick this up later in the course in thermodynamics. And then the molar mass. When I looked at the molar mass for a nitrogen-oxygen atmosphere, it works out to be almost exactly 29.0 grams per mole. And that is 0.0290 kilograms per mole. So I put all those numbers together. I found out that the scaling factor, which tells me the rate at which pressures drop off, is 8,000 meters. Now, what does that mean for an exponential? So the scaling factor tells me the height, in this case. It tells me when the function drops to 1 over e of its original value. Now 1 over e, the natural base, is about 37%. So it tells us by the time you've gone up 8,000 meters, the air pressure and the density of the air has dropped to about 37%. Okay? This is an exponential drop-off. Now you guys are probably familiar with things like half-life, where you know, after a certain time, half the stuff is gone. Well, this is not base 2, this is base E, because that's the natural base to use. And after one scaling factor, we'll be at 37%. Now I'm going to come back. Every time we run into an exponential, we'll go through and talk about this a bit. But I really, really think it's important to be familiar with exponential functions and how exponential drop-offs or exponential rises work. It's really unfortunate that in common language, if you watch news programs, people throw around the word exponential all the time. Exponential means something in particular, and it doesn't necessarily get used appropriately. Anyway, so in science, exponential functions show up all over the place. So you want to be familiar with what an exponential, what its properties are. And again, for base E exponential drop-off, one scaling factor, A, is going to drop us down to 37%. Two of those would drop us down to 37% of 37%, which is about 14%. And then three of those drop us down to about 5. So what that tells us is if I go up just 8,000 meters, the atmosphere is already down to about 37% of the pressure at the surface. If I go up an additional 8,000 meters, that actually drops me down to about 14%, and a third, 8,000 meters, 24,000 meters, I'm down to about 5%. So you can see that the thickness of the atmosphere drops off really quickly. Now, 8,000 meters is about 26,000 feet, and there are mountains of this height. And so this is roughly like Mount Denali or something, right? So if you get to the top, the air pressure is only 37%. Yes, you can still survive. Your water, your bodily fluids will not vaporize until you get to a much lower pressure. But you can see how much of the air is no longer there. So I did do a scaling factor to see how far we would go up until we only have half of the air pressure, and that happens at about 5,550 meters or 18,200 feet. Now for myself, the highest elevation I've ever climbed to or hiked to, just kind of a walk-up, is Mount Wheeler in Nevada near the Utah border in Great Basin National Park, and that elevation is about 4,000 meters. It's just a little bit over 13,000 feet. So putting that number into the exponential drop-off, at that elevation, the air pressure was down to 60%. So only 60% of the same pressure that was at the surface. All right. Okay. So kind of interesting, and I think important that people have an idea about properties of pressure and density and how that drops off with distance. All right, we talked about this a bit before. We talked about gauge pressure versus absolute pressure. Now, gauge pressures work this way. At sea level, atmospheric pressure is 101,300 pascals. This is referred to as 1 atmosphere of pressure. Another unit of pressure, now this one I have mixed feelings about, is the bar. Now, the bar is almost equal to 1 atmosphere, but the bar, we say, is exactly 100,000 pascals. Now, I always feel like we don't need both units, the atmosphere and the bar. Maybe we should just do atmospheres instead of bars. Anyway, this is a direct factor of 10 multiple of pascals. Now, standard atmospheric pressure is just over 1 bar. Now here, again, they say the pressure does not crush us as our cells maintain an internal... I think that's kind of a funny thing to say. It's not that our cells maintain some kind of extra pressure to survive. It's just everything is at that pressure. This textbook is compressed due to air pressure. If we got rid of the air pressure, it would uncompress just a bit. Everything around here is compressed due to background fluid pressure, and that's just a part of being anywhere where gravity is, squeezing this stuff together. And so the pressure is essential. I mean, everything that we do, the cells aren't doing anything in particular to offset the pressure. They're just dealing with the pressure as is. Everything evolved with that pressure in place. And again, if you took away the pressure, the water would go back to vapor. It would not remain as a liquid. Okay. So now, getting back to the gauge pressure, so the absolute pressure that we measure is taking gauge pressure and then adding in the background atmospheric pressure. Just a reminder. Okay, and here is a list of pressure units, and this drives me just a little crazy. You think the best way for all of us to be kind of on the same page is to work with a limited number of units. Let's not use so many different units that we've got a different unit every time we measure something. So let's see, which ones do you guys want to keep? In terms of pascals, 1 atmosphere is 101,300 pascals. I'm okay with that. The bar, I don't think we need both of these. Maybe get rid of the bar. Now, the dyne per cubic centimeter, that's actually just a different set of standard units that get used. So rather than using meters and kilograms, we use centimeters and grams. So maybe we keep that. I mean, the pounds per square inch, probably don't need those. Here's actually the one that drives me crazy the most, is the millimeters of mercury. Oh, come on, isn't that a little past, isn't that a little archaic that we're still using millimeters of mercury? I don't mention this at my doctor visits. I know I should. I should say, really? Millimeters of mercury? Can't you tell me what my blood pressure is in pascals? Pascals would make a lot more sense than millimeters of mercury. And so I would eliminate the centimeters of mercury, the millimeters of mercury. The torrs are just millimeters of mercury. And then millimeters of water, that's kind of the same thing. So I would say gone, 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 gone. Yeah, maybe. Anyway, that's my personal preference. You guys may feel differently about some of these units. Okay, now here is the reason we use millimeters of mercury, so there's a historical basis. But I don't think that's a reason to keep the units around. So this is a barometer made out of mercury, which is not healthy. So when I was, as a kid in high school and college, and all of my science classes, we had these mercury barometers at the side of the wall in the classroom, and you'd walk over there and you would look at the barometer, the mercury barometer, this big tube filled with mercury, to find out what the pressure was for the day. What pressure should we put in for the whatever experiment we were running for that particular day. It turns out that if you take a tube, now notice it's closed off at the top. So you take the tube, you fill it with mercury, you flip it upside down so that there's no air. That means there's no air pressure. Now, you flip that over, you put it in another puddle of mercury, and there's air pressure here. So at this level, there is 1 atmosphere of pressure. And what the question becomes is then, how far up this tube will 1 atmosphere of pressure push the mercury? And it turns out that 1 atmosphere is enough to push the mercury up to 760 millimeters. And that's how these barometers work. Okay, and so let's see if we did the same thing with water. What if instead of using mercury in here, what if we used water? Again, there's a vacuum in here. The way the formula works is we take delta P is equal to density GH. That was what we've been looking at. So the height then would be delta P over the density divided by the gravitational field. Now the pressure we're measuring is atmospheric pressure. Here's the gravitational field. The density of water is 1,000 kilograms per cubic meter, and that gives us a height of 10.3 meters. That's a really tall barometer. So that would mean going up to like the 3rd floor to read the barometer. So that's not convenient. Now mercury has a density that's more than 13 times higher. Now I did the calculation, and I think I had a good density value I looked up. Anyway, I ended up with a height of 764. I'm not quite sure why that didn't come out at 760. Anyway, it worked out to be a column of mercury at 764 millimeters is enough to create 1 atmosphere of pressure. So maybe we'll take a break here. I just wanted to show this one picture. Here is a water barometer, and the water barometer is being held in place by these supports. And this is a Torricelli style barometer. So they got a bucket of water, a pond of water down there in this tube, and it's 10.3 meters high, right? So that's how high the water barometers would need to be. All right, yeah, let's go ahead and take a break right there, and then we'll come back.